Now that we've sort of gotten some good definitions and some foundations in what functions are, we can start to sort of talk about the formalities behind graphing the functions, right? If you recall when we were talking about lines, um, I kind of said that part of precalculus is taking these objects in the plane and seeking to describe them algebraically. Right? We take these lines and these parallel lines, these perpendicular lines, and we put algebraic equations sort of onto them to model them. Well, it turns out we can actually go the other way. We can take these algebraic objects that we've been talking about, right? These functions, and we can graph them, right? So let's throw down a quick definition, right? So say if f is a function with domain A, and we'll say that A is a subset of the real number line, right? So it's just some set of numbers, right? Um, then the graph of f is the set of ordered pairs and we'll write down our set. It's the set of all x, comma f of x, where x is in A, right? And like sort of quick note, right? If we assign a dependent variable for y, right? Um, if we assigned that, right, then the graph of f, it's the same as the graph of the equation y equals f of x, right? So hopefully that sort of clears up the distinction surrounding like the difference between f of x and y equals something. Um, we're just using a function to define an equation which allows us to graph it, right? Um, speaking of graphs, right, we can have, our coordinate plane, right? Because all of this is taking place in the coordinate plane. And we can have some set A, right? We said that A is a subset of the real numbers, so say that this set here is A. And what we do is to each point in A, we use our function to assign another point in the real numbers, and we can sort of plot all of these points. And if we're doing on all of A, then it might look something like this, right? Where these are our endpoints, and if we have some point in our domain, say little a, then the point on that graph would be f of a. Or if we have some point over here, say little b, then the point that maps to would be f of b, right? And this is very theoretical, right? So let's try some more specific examples, right? And I know that in your high school math classes, you totally would have seen graphs of functions like this. So I'm going to hopefully go through it rather quickly. Um, so let's just throw down some examples, right? Let's say we have f of x equals x squared, right? And the main way that we have to go from this function to the graph is just by plotting points, right? We pick a few points in the domain that we think will give a good representation of how our graph is behaving. We run them through our function, we plot them in a coordinate plane, and we connect them with some sort of smooth line, right? So we have our little table of x's and f of x's, and we pick some points, and I suppose we'll also need a set of axes, right? So let's say, I don't know, let's say they look like this, where I'm actually going to move this down a little bit because x squared tends to get pretty big. Okay, so, the first kind of common sense point to plot would be, what happens if x is 0? Well, 0 squared is 0. Okay. If x is 1, I guess I should plot that point right. That's 0, 0. If x is 1, 1 squared is 1. So the point 1, 1 is on our graph. But what if x is negative 1? Well, if x is negative 1, then negative 1 squared is still 1. So I guess I can put a plus or minus there. Okay, what about if x is 2? Or negative 2, right? Because as we just saw, it doesn't matter which, whether we're positive or negative, when we square it, it's going to be the same. And positive and negative 2 squared would be 4. So if we go over 2, we should go up 1, 2, 3, 4. And for good measure, if we're, say, doing, plus or minus 3, then we would go up 9, right? So that's 4, and we'll count up 5, 6, 7, 8, 9, and so our point should be right there, this guy right there, and it should be modeled over there. And now, as I said, we connect these with a nice smooth line. Something a little bit like that. Okay, well, what about, I don't know, let's say g of x is x cubed, right? We put down our little table, f, or x and g of x. And as always, we might start with 0. 0 cubed is 0. Let's draw our little line here and do something like that. So we know that 0, 0 is on this. Okay, well, what about 1/2? Well, 1/2 squared, or 1/2 cubed, sorry, is 1 over 8. So if we go out, say this is 1/2, we're going to go up an eighth. So just a little bit, right? Half of a quarter. Well, if x is negative 1/2, then when we cubed, right, that negative 1 actually stays. So we get negative 1/8. So we're going to be about there. If we're at 1, 1 cubed is 1. And if we're at negative 1, well, negative 1 cubed is negative 1. So we're going to be there and there. And then we'll, throw down 2 more. Let's say 2 and negative 2. Actually, let's change the scale on this, right? Let's make that 1, right? So on the x-axis, right, we have a scale of 2 dots is 1, and on the y-axis we have a scale of 1 dot is 1, totally allowed, right? We do need to move that down there. 2 cubed is 8, which would tell me that negative 2 cubed would be negative 8. So we need to count up 1, 2, 3, 4, 5, 6, 7. Looks like I just made it with 8. And 1, 2, 3, 4, 5, 6, 7, 8, just like that. So our, graph of x cubed is where I smoothly connect all of these dots. And unfortunately, my hand is not the smoothest, so you'll have to forgive me, but our graph is going to look something like this. This side, I will say, looks much better than this side, but it's the thought that counts, I guess, right? We'll do one more of these. Let's say h of x is the square root of x, right? And we'll throw down some axes, maybe a little something like that. So we need our table, x and h of x. And we want to, again, pick a few representative points from our domain. But our domain here is restricted, right? Even though, it wasn't restricted on f of x equals x squared or g of x equals x cubed. Both of those have a domain of the whole real line. But this has a restricted domain, right? So we can't pick numbers that are less than 0. We can, however, pick 0. So let's start there. As we've said, the square root of 0 is 0. We can say try 1. The square root of 1 is 1 again. And I don't know, let's say the square root of 2 The square root of 2 is about 1.41, but we'll just write the square root of 2 here and draw it somewhere around there. Skipping 3, what's the square root of 4? Well, the square root of 4 would be 2, so by the time we're at 4, we're all the way up to 2. And I think we have enough information to sort of get an idea of the trend here, and the trend of this graph is to do a little something like that, right, where it's going to continue very slowly up and to the right. So we've seen, this sort of nice way to graph these sort of nice functions like this. But what if we're doing something with, say, a piecewise function, right? Let's say the piecewise function f of x, let's say it's x squared minus 3 if x is less than or equal to 2, and x if x is greater than 2. Right, let's sort of do the same sort of idea, right? Let's plot a representative sample of points and see if we can, work out a way to graph this. So I'll throw down my axes. Let's say they look something like that. And we need a column for x and a column for f of x. Well, as always, let's start with 0. At 0, we're in this part of the domain. Okay, so that means we need to do 0 squared minus 3, which is negative 3. Let's say at 1, we're still in this part. And so at negative 1, we're still in this part as well. And so we can use our little trick of 1 and negative 1 squared is the same. So that would look to me like that would come out to, on our inputs of plus and minus 1, we're at negative 2. And if we're at negative 2, well, if we're at negative 2, we're still here. So negative 2 squared is 4. 4 minus 1 is positive 1. But at positive 2, well, we're still there, right? So positive 2 squared is 4, minus 3 is 1. But watch what happens when we do 3, right? Positive 3, now we're here, so the output is just 3. Okay, well, what about negative 3? Well, negative 3, we're still going to be here. 3 squared is 9, minus 3 is 6. And I think we'll have sort of enough of an idea to get the behavior of this quadratic. So, 4, well, we're here again, so our output would be 4. And with this big sampling of points, let's put them on our graph. So we know 0, negative 3 is on it. We know that at plus and minus 1, we're at negative 2. And we know that at plus and minus 2, we're at 1. Okay. At negative 3, we're at positive 6. So 1, 2, 3, 4, 5, 6. But at positive 3, we're at 3, which is there. Positive 4, we're at 4, and so on. Now, you might be tempted, as we did before, to smoothly connect these with some sort of line. But in a piecewise function, that doesn't actually quite work, right? Now, within each of these pieces, we can, but not when we're dealing with the whole thing, right? So on this part of the domain, I can connect this with a smooth line, right? So if x is less than 2, I can connect all of this with a smooth line. Let's see how well I do. Again, I'm not famous for doing the best job at that, but let's say it's going to look something like that. And I know that on this side, this is going to continue up like this. But now the obvious question is sort of what happens here, right? Well, if we're greater than 2, we're on this line, right? The moment we're equal to 2 or less than 2, we're on this parabola. So the way that we, no, so the way that we sort of denote that, right? If we come as close to 2 as we want without getting to 2, we're on this line. But when we're at 2, we're not on that line. And the way that we denote that is we just put a little circle right here, right? To say that all the way up to that point, we're kind of heading toward it. But at that point, we're not there. One more piecewise function for you. As we saw in the last lecture, we have g of x is the absolute value of x. Well, we can split that up into it being x if x is greater than or equal to 0, or negative x if it's less than 0. So, what does this graph look like? Well, again, let's plot some points, right? If we're at 1, we just output 1 because 1 is greater than 0. If we're at 0, well, we output 0, right? Because we're just outputting what our input is, right? So if we're at 2, our output is 2. If we're at 3, our output is 3, and so on. And I feel confident enough to connect this part of this piecewise function with a line like that. Okay, well now what about this side here, right? If my point is at -1, well then I go up 1. If my point is at -2, I go up 2, and so on and so forth. But my question is what happens right here at 0, right? You'll notice here we sort of drew this open circle, right, to denote that as we approach there, we never quite get there, but that's where we're headed. Well, that would tell me that, as I approach this way, we never quite get there, right? Because this is a less than. We never quite get there. But wait, the place that we're never quite getting but almost there was the same place that we're here on, where we're equal, right? This sort of approaches 0 as we move this way. And so does this, right? This approaches 0 as we sort of walk this way. So we don't need to draw the circle here because, well, the place that it's approaching is actually where it equals right there. So one of the biggest differences, right, between this one and this one, besides the fact that we have a parabola here and a line here, is here we have this big jump, and here we don't, right? And that sort of gets at this idea of something called continuity, right? And what continuity just means is that you can put your pencil down or pen or, whatever drawing instrument you choose, and you can draw the whole graph without picking it up. So there's no sort of breaks, there's no sort of holes. If I have, say, 2 sets of axes here, right? I can draw this, graph without picking up my pen, right? So this is a continuous function. Versus, if I say draw something like this, that is not a continuous function because there's this jump right here, right? Also not a continuous function is if you were to have something like this, right? It's constant everywhere except for right there where it has a hole. And what that means is at that point, it's undefined. But if I were to try and draw this, right, technically I would have to pick up my pen right here, right, because it's undefined there. Since it's undefined right there, I can't draw continuously through it, so this is not a continuous function. Things like this, right, where you have these like sharp turns, those are totally allowed, right? Those don't break continuity. So we can sort of go from a function to a graph, right? But what about the other way, right? Can we, given some sort of arbitrary graph or curve, right, can we determine if that's the graph of some function? right? Even if we can't necessarily write that function down, right? One of the things that you may have seen me do a lot, right, is I'll kind of draw these axes and I'll, just draw some sort of little squiggle on it, right? Given any sort of squiggle curve, like, whatever you want to call it, can you always find a function matching that? And if you recall what we said about a function, right, it will kind of give you the answer, right? A function has one output per input. So the question is, how can we formalize that idea and use it in terms of a graph, right? What does having more than one output per input look like on a graph? Well, it would mean that if we look at, say some point, well, then there would be 2 points assigned to it, right? So if we took a vertical line like this guy and sort of swept it across our function, at any point this vertical line would only cross our function once, or our graph once. And if it passes that, well, then we're dealing with a function, right? So this would appear to me to be a function, right? Versus if we say did something like, this, right? Something like, I don't know, this, right? If we take our vertical line and we sweep it across, we're good here, we're good here, we're good here. Then all of a sudden, as soon as we hit right here, well, this isn't a function anymore, right? Because look at this, we have 1, 2, 3 outputs for this input. So this curve, right, this isn't a function, right? This is what we call the vertical line test, right? So the vertical line test states that a curve in the plane is a function if and only if, right? Notice that it uniquely determines whether or not it is or isn't, right? That a curve in the plane is a function if and only if um, no vertical line intersects the curve more than once. Or, kind of put in more human terms, if I sweep this vertical line across the curve, it only ever touches it once, right? So let's do some more examples, right? Let's say, what about this curve here, right? If we have this curve here, well, I can take my vertical line and as I sweep it across, we're good and we're good and we're still good here, even though there's this sharp corner, and we're good all through that, right? So this red jaggedy thing, that's a function. Something like, say this, where we, maybe go like that. This guy, we sweep it like this, but as soon as we get to this loop here, well, now we're hitting 3 points for the same vertical line, this guy right here. So this also is not a function. Okay, let's, maybe do one more, right? What about this guy right here, right? Let's say we, I don't know, let's say we just kind of draw an ellipse, right? Well, if we take this ellipse, we kind of take our vertical line and move it across. At every point on this ellipse, actually, we're intersecting more than once. So this curve, this ellipse, also not a function. Okay, so, we can go from a curve to determining whether or not it's a function. But remember, all of these curves are the set of solutions to some equation. Say we have some equation like y minus x squared equals 0, right? The question is, can we take this thing that is an equation and transform it into a function, right? Can we always uniquely solve for y? Well, in this situation, it's pretty quick to see that this is the same as y equals x squared. So we're good, right? We formed a function out of our equation. So that would mean that this equation has an equivalent function. Um, and we can sort of do that whenever we have an equation that involves y, right? So, very similar to this, let's say we have y plus x squared equals 2. This is an equation. If I subtract x squared from both sides, well, that would give me that y is 2 minus x squared, which is good, right? We have now taken this equation that involves y and transformed it into a function of x. So this is indeed a function as well. But what about something like this, right? What about, say x squared plus y squared equals 4? Well, if we have x squared plus y squared equals 4, we can attempt to solve for y by first moving x to the other side, right? We have y squared is 4 minus x. Well, but now if we take the square root of both sides, that would tell me that y is plus or minus the square root of 4 minus x squared. That should be a squared. Well, now this is a problem, right? Because for each input x, I get plus the square root of 4 minus x squared, and I get minus the square root of 4 minus x squared. So this is not a function. And it's not a function because remember, one of the things that defines a function is that it's one output per input. And I feed in one input, x, and I get two outputs, so we don't have a function. Those of you who remember your conic sections, if you ever studied those in high school, you might recognize this equation as the equation for a circle with radius 2. And if we bring back our vertical line, right, and we attempt to sweep this over, you'll notice, well, it also fails the vertical line test, right? That's the nice thing about this vertical line test being if and only if, right? As long as you have this graph, you can always tell if there's a function of it, but it's not necessarily always possible for us to solve for y, right? That's why this vertical line test is so important. As we finish up this lecture, we have sort of one more thing to look at, and that's sort of getting a handle on the sort of archetypes of functions that we're going to be dealing with. And there's 5 main functions that we'll work with for the most part. I don't usually try to do this in these lectures, but I'm going to pull some editing magic to sort of throw up the information about these functions. All right, with that sort of movie magic behind us, I sort of have a template for us to do some work on. And we're going to look at sort of some of the common functions that we will run into a lot, right, sort of throughout this course. And it's just helpful to kind of know their basic structure so that we don't have to always plot a bunch of points, right? And we can get the idea of a graph down when that's all that matters, right? Obviously, there's lots of times where you do want the specific points and all that, but there's other times where we just need the gist of a parabola in a certain area, and so it pays for us to know these common functions and their graphs, or another way to refer to these are the sort of parent graphs of these systems. And as I said, they're sort of broken down into 5 archetypes, right? The first one of these are the linear functions, and they look like f of x equals mx plus b, right? Their graph is a line, hence being linear. And there's sort of 2 that I want us to take a look at. One is just a specific case of the other, right? That specific case, if we have f of x is equal to b, right? No matter what input you put in, it's going to spit out the output b. I'm going to actually change that to blue. If f of x equals b, well, then my graph, I'm going to use red for the graphs. My graph is just a constant graph like that. No matter what input you have, you have the output b. The more general case on this is, say if f of x is mx plus b, and we looked at this earlier in the week, right? That is some line in the plane with the y-intercept of b and the slope of m. The next archetype is called the power functions, and the sort of large-scale form of the power functions is where f of x is equal to x to the n, right? Where n is a strictly positive whole number. And so these are things like f of x equals x squared, right? This is a parabola. And the graph of our parabola looks something like this, right? It's gonna, be really steep out here and really shallow as we approach 0, and then it's gonna be shallow for a bit, and then it's gonna get steep, right? Similarly, say f of x cubed, right? What's f of x cubed going to look like? Well, for f of x cubed, we know it's going to hug the x-axis a little bit closer and then get a little bit steeper. And it's going to do the opposite on the negatives, right? So this guy is approximately what an f of x cubed will look like, although I will move it down just a bit because it's going to pass through the origin. Something like f of x equals x to the fourth. Since f of x to the fourth is the square of x squared, it's going to resemble this parabola a bit. So it does just like a parabola, kind of do this, but it's steeper out here and it's even closer to the x-axis near 0. One bit of nuance here. It looks like a steep parabola, but it is not a parabola itself, right? It is a quartic function, right? Because it's the fourth power. Our fifth degree function, just how the fourth degree looks like the second degree, but hugging a little bit closer. Same thing for the fifth degree, right? If we have f of x is x to the fifth, well, then our graph is going to look something like x cubed, but hug a little bit closer. Okay, our next archetype are what's called the root functions, right? And these are everything that looks like f of x is the nth root of x. Starting off, right, let's say f of x is the square root of x. Well, we already graphed this earlier, right? This is going to look something like that, right, where it's going to continue arbitrarily far this way. What about the cube root of x, right? What if f, matching colors, what if f is the cube root of x? Well, if we're in the cube root of x, our function is actually defined on negative inputs. So it's going to look a little bit something like this. In fact, it looks a lot like a cubic function turned on its side. We'll sort of study that a little bit later next week, probably. The fourth root, in a similar story that we'll kind of see again and again, the fourth root of x, since it's the square root of the square root, is going to look a lot like the square root function, but it's going to hug the y-axis a little bit more and be just a little bit flatter. And as you would expect, if we were trying to graph, say, the fifth root of x, well, it's going to look something like the cube root, but it's going to be a little bit flatter and hug the y-axis just a little bit more. In fact, I'm actually going to redraw that so it hugs this y-axis even tighter, right? So the fifth root's going to look something like that. Again, these are sketches of the graphs, right? We're not worrying about the specific points. We're trying to get a handle on the general shape of these types of functions, right? These sort of archetypes, these parent graphs. The penultimate archetype are all of the things that look like f of x is 1 over x to the n, again, where n is a positive whole number. And these are things like, say f of x is 1 over x, right? That's going to look a little something like this. Perfect. Okay. Um, Now I'm sure you're guessing what's coming, right? What about f of x is 1 over x squared, right? Well, this is going to look something like our graph of 1 over x, except because of this square here, we're never going to get negative numbers, right? So this is going to hug the x-axis just a little bit tighter, and the y-axis. But everything's going to be positive, right? So it might look something like that. We will absolutely explore these reciprocal functions later in the quarter. Next up, let's say f of x is 1 over x cubed, right? Well, we're multiplying by another power of x, so we are allowed to have negative outputs now, and because we're doing x cubed, we're going to hug the x and y axes a little bit tighter, but we're going to be, on the positive and negative outputs. Our final one for this archetype, say f of x is 1 over x to the fourth. Following the same story, it's going to look a lot like x squared, but a little bit tighter, maybe something like that. The final archetype that, just sort of barely makes it in because we see absolute values a lot, so it deserves to be mentioned here. We've already graphed this. It looks like this, right, where you have a line like that, going up and to the right and up and to the left on each side. So believe it or not, that actually completes all of our instruction for week 2. Your homework should already be up if I'm doing things on a timely manner. And next week, we're going to continue our study of functions and actually hopefully wrap up chapter 2. So I'll see you then.